Okay, over to you, Barney.
Thanks, Frank, and thank you very much to you and the university for inviting me to give this talk. It's a pleasure to be here. It's nice to be talking about some aerodynamics, and really, for me, it's an opportunity to share some of my knowledge and experience, really. Today is going to be a bit of a whistle-stop tour of aerodynamics, really in terms of the bit of background of the theory, and then onto application, and kind of bringing those two together, really from an applied perspective. So what can we learn from the evidence and the literature, and how can we apply that? I'm not going to be comprehensive, because an hour is not large enough time period for that, but just to give you a bit of a introduction to that area. So in terms of a little bit about my background, really, I've been involved in performance sport probably since about 1997. Just after I left university, got involved with the changing culture in the UK around funding on Olympic sports. My initial sport as a background was sprint kayaking, and I worked in that sport for many years. And so overall, I've probably had about 13 years full-time working directly with sports performance. And that's where I came across Giles Warrington, the head of department at Limerick. And I stayed in that sport for quite a long time. But I had a building interest in cycling, mainly from a personal point of view, but also from a scientific point of view. And I got involved in understanding more about fluid dynamics from a kayaking perspective and a canoeing perspective, but also in terms of a cycling perspective. And so I kind of started my involvement with fluid dynamics probably in around the year 2000, really. And I currently hold a joint role in terms of an academic position at Leeds Beckett University in our Carnegie Institute, along with work with external partners and sports and all the rest of it. And just some of the groups I've worked with there over the years, and built experience of working both in industry and with high performance sport. And so hopefully today I'm going to give you a bit of a background on the aspects of aerodynamics I've been working with. In terms of what we're going to cover today, we are, as I said, it's really around this kind of applied perspective of how we can translate some of the science and understanding and the physics of aerodynamics into real world interventions for athletes. We're going to cover a little bit about drag forces in cycling and the various methods there are to measure aerodynamics, and then looking onto some of the key kind of considerations in terms of positions that we might get on the bike and work with athletes on. There is a quite an interesting history of aerodynamics in cycling. As you can see here, this is a bit of just a chart really, which tracks the distance in the hour record. So the hour record is usually like the pinnacle of aerodynamic development, or regarded as such. This is just the men's data, so apologies for that. But it's a good representation overall of our kind of understanding and application of aerodynamics in cycling. So in the early years of the century, when it kind of started, the predominant changes or increases in performance, the distance travel, was primarily due to improvements in physiology and training and that knowledge. And then it was really kind of the 90s really where we started to see, in late 80s I suppose really, with Laurent Fignon and Greg LeMond, starting to see the involvement and importance of aerodynamics in cycling, how much of an impact that can have on speed and therefore distance. And those of you who can remember, back then you might have come across this kind of this battle between Graham Abbree and Chris Boardman around different positions, trying to go further and kind of one-upmanship. And that kind of that was all around development of aerodynamics and aerodynamics knowledge and reducing aerodynamic drag and the requirements to overcome the power requirements to overcome that drag. And that led to a kind of a ban of some of these more aerodynamic positions. And you can see on that chart, when that ban happened, then all of a sudden the kind of the distance dropped down. And then as we've kind of, again, more recently, in the last kind of really 10 years or so, have developed our additional knowledge around aerodynamics within the constraints of a kind of a more standard time trial bike. You can see there's been some improvements, and where we are currently, with this image on the right with Felipe Ganna, with a current record of 56.72 kilometers an hour. And really now aerodynamics and the kind of the drive for reduction drag looks at every aspect of the bike and the rider and position and equipment and skin suits and all those kind of things, looking at all these different ways and understanding the kind of the physics of aerodynamics to reduce drag. So just very basically, really, when we look at the power that's required to drive the bike at a certain speed, there's a number of different resistances that are going on. So we have wheel bearing drag. So if you look at the end, at the bottom there, we've got speed and power requirements. So as we increase in speed, there is an increase in the resistance associated with wheel bearings, but it's very small, but it does increase. Okay. The next kind of resistance force in terms of the magnitude is rolling resistance, and this is really to do with tire pressure, tire design, construction, and again, as we increase in speed, the power that the cyclist is required to overcome that aspect or that proportion of the rolling resistance increases a little bit as well. You can't see it so much on this scale, and it can be important at certain speeds for certain events, particularly high level competitions. And then the next one, really the biggest one, the primary area of drag, is this aerodynamic drag, and you can see how much of a proportion that is here, and it kind of grows at in a power function effectively. So if you take an example here at 34 kilometers an hour, at that point, at that speed, 17% of the kind of power demands are to overcome rolling resistance, 1.2 bearing resistance, and then you've got 68% of the power is there to overcome the aerodynamic resistance. And then if we increase, again, just take another example, say 50 kilometers an hour, which is very close to the kind of speeds that occur at kind of the top end of the sport, depending on the distance. So to give an idea, there you can see the rolling resistance has increased to a proportion of 9%. I mean, everything's increased, but as a proportion, rolling resistance is 9%, bearings is 0.7 now, and obviously the largest drag that we need to overcome is aerodynamics. So we can see the relative importance of it, and hence the drive to try and reduce aerodynamic drag where possible in a strive to improve performance. And so just as a kind of a generalized comment, that across a range of speeds, and depending on the gradient, that's kind of the range of the drag, the aerodynamic drag accounts for in terms of the power demands. Another way of looking at this as well to understand the importance of drag is we have this value called CDA, which is a measurement of essentially how slippery someone is. If you think about someone traveling through the air, a low CDA value, and we'll get onto exactly what that means someone creates less aerodynamic drag than someone with a higher CDA value. And across the top there, we move from left or right to left, a CDA of 0.3 would be someone in a very kind of a standard kind of road bike position, up on the tops of the bars, but still with kind of cycling clothing on, still in a normal kind of cycling position. And then as we track down, this is more about moving into time trial position. 0.25 would still be a reasonable time trial position. 0.21 would be a very good time trial position with all the right helmets and clothing, wheels, all that kind of thing. And then 0.18 is kind of the lowest you get. You do get occasionally a little bit lower than that, but it's with an awful lot of refinement. But here you can see, if we just run some scenarios, is that if you had an athlete or a cyclist who's limited to power, as most of them are at some point, if you have a time duration where you're trying to travel as far as you can for a 30-minute period, or say a 25-mile time trial, which might take sort of 50 minutes or so, usually you've got a ballpark area of what your sustainable power output is for that period. So let's say it's around, for argument's sake, it's quite a good value, but around 400 watts. Well, at 400 watts, if you're in a normal kind of cycling position, road bike position, that kind of blue chart, I don't know if you can see can you see my cursor on there? I'm not familiar with Zoom. Yeah, you can. So at 400 watts there, you can see that actually that would give you a kind of an average speed of 45 kilometers an hour. If you then change your bike, change your position, got in some better kit and worked in position, now that 400 watts is sustained might be somewhere up here, in these kind of values, which is close to kind of 50, 51, 52 kilometers an hour. So pretty quick. So you can see how quickly a change in your aerodynamics, or reducing your aerodynamic drag, can have a big impact on your velocity. And these are all kind of simulations that really work. This is where kind of applying physics and mechanics to a real world solution can is surprisingly straightforward, actually, and surprisingly accurate as well. So we often do a lot of modeling and this kind of modeling approach within cycling. So if we think about what actually determines this power that we require to overcome drag, so what are the components of an aerodynamic drag from a cycling perspective? Well, there's an equation here. Don't know how familiar some of you are with these kind of equations, but effectively it's telling us that the power to overcome the aerodynamic drag, this PA, is a function of the speed you're going at relative to the air, because we always have to think about being the relative airspeed, because if you're outdoors, there might be a wind, it might be a headwind, it might be a tailwind, and the forces required to overcome the drag. So, and then if we break down that even further, then we can see that actually that's comprised of the coefficient of drag, which is a measure of how slippy you are. We'll get onto that, or the shape is the area that is, and literally the kind of the frontal area that's facing the wind, the air, and then we've got half of the air density, and then obviously we've got the relative airspeed cubed. So that's the equation. We can start to pull out little bits, but basically it's telling us that we've got the air density is important, coefficient of drag is important, and the area that's presenting to the wind is important. So through these three sections. So as I said, the coefficient of drag is really the shape that faces the fluid flow, and obviously in a bike, you can, when you're cycling, you can change the shape, as we'll see, but also we don't necessarily just think about what that shape looks like from the front. It might be actually that when you take all the winds into account, the actual shape that's facing the relative resultant wind direction is actually slightly side on. We talk about a yaw angle, and often this can be quite high, particularly if the strong side winds and crosswinds can be up to sometimes 10 degrees, but not often much more than that. The coefficient of drag also depends on the surface characteristics, literally of the objects, either the bike or the body, the clothing. The frontal area is that cross-sectional area facing the fluid flow. And then the air density is a really critical one. And that's obviously something that will change from day to day, venue to venue. It depends on the environmental factors and really of pressure, temperature, and humidity. Some of the hour records are actually, obviously people go to altitude to try and break those records, because obviously at altitude you have a lower air pressure, which will reduce the air density. Temperature plays a role, as does humidity. And just so you're aware that actually humidity is an interesting one, because we often think that when the air is very humid, it's very thick, kind of soupy-like liquid that we move through. But actually, because a water vapor molecule weighs less than an oxygen molecule, when it's humid and we get these water vapor molecules in the air, they effectively push out the other molecules. So it's like an equilibrium depending on pressure. And so that air is actually has less mass, which makes it less dense, so easy to go through. So in terms of outdoor records, then actually you want a humid day, or outdoor cycling, if you want to go fast, you're really after a humid day and a warm day, and somewhere where the actual environmental pressure is quite low as well. So all these environmental conditions will give you an environment. So when Bradley Wiggins did the hour record in I can't remember now, actually, 2014, 15 was it? They actually heated up the velodrome inside to increase the temperature to reduce the air density. So a little bit background there. In terms of the other type of the actual drag forces that are created, it's really down to this airflow. So we talked about the coefficient of drag and the frontal area as being those two things, the CD and the A. Well, in terms of the CD, the coefficient of drag, this is all determined by what happens to the actual flow around the object. So in our case, it's the bike. And the majority of the drag forces that are created is pressure drag. So a very kind of a low drag object like an aerofoil would have a low pressure drag acting on that object rather than, say, just a cylinder which isn't as shaped. And effectively what we're trying to do when we're working with cyclists and trying to improve their position is to try to effectively reduce this pressure drag. So one thing is to reduce the frontal area. The second thing is to increase the pressure on these rearward facing surfaces. So that means what we're trying to do is essentially extend the length and the shape of that object, so there's not a sudden drop off in terms of drag that's occurring, so we don't get this turbulence. And that's really what we're trying to do. We're trying to keep the air attached to the body or to the surface, and we can do that by the shape of it, trying to make the shape longer and rounded, which we can't do very easily in cyclists, but we do get some of that effect by changing the orientation of various things or different helmets. The next one we can do is to reduce this stagnation that we get, so to keep the air flowing. And sometimes what we get is situations where literally the air molecules will kind of they'll hit the surface and they'll kind of stagnate, they'll get trapped, and then that in turn creates turbulence. So what we're trying to do often is create trips or rough surfaces to effectively keep this going, create a bit of a keep the flow going, create a boundary layer in order to ease the flow of air around the body without creating lots of turbulence, big areas of turbulence and these differences in pressure. We can also do that through clothing. So in cycling, clothing is really important. And those of you who follow cycling quite closely will have seen the development in some of the skin suits and the materials. So when we do develop skin suits, actually material testing and looking at the drag characteristics in certain situations is really important as well. And I've been involved in some of that development before. And if you're doing all these things right, then you can have a huge impact on that coefficient of drag and therefore the total area. Here's an example of the role of kind of helmets. So you can see from get an idea here from the colors, what's happening in terms of some of the flow and the levels of fast flow and low flow. And what you can see here, if you take the kind of the top row, if you like, you've got two types of helmet, a more kind of aerodynamic long-tailed helmet on the top left-hand image. On the right-hand image, this would be a more standardized road helmet without much of a tail, without much of an aerodynamic tail, maybe a very small one. And the depiction of the blue and green lines, so this is from CFD, computed flow dynamics data and simulations, you can see we're starting to get some of that turbulence, and that's going to be cause quite a lot of drag, but it's not too bad in that situation. But in cycling, we don't always hold our heads in that position, and often heads are dropped, they get fatigued, we have to move our heads around to look where we're going, all those kind of things. And so what can often happen of the bottom left-hand side is you get a bit of a penalty in this case, in that although on the top left you've got really good aerodynamics with none of those blue and green kind of lines occurring at the bottom, well, all you need in this scenario is a drop of the head, the tail of the helmet lifts up, and all of a sudden you've got huge amounts of kind of stagnation. That slow moving air creates turbulence and an awful lot of increase in drag. Whereas the other helmet, the one without an aerodynamic tail, while it might not be quite as aerodynamic in that standard position, the ideal position, actually when the athlete looks downwards to see where they're going or something else, there is no tail, and the drag, yes, it gets increased, as you can see by the green and blue lines, but it's not that dramatic. So the changes in drag are not that great. So here's a scenario you've got to think about, or an athlete needs to think about. You know, are they in a situation where they're going to be moving their head around a lot, or can they stay in position? And that would make an impact on the choice of helmets. And a lot of helmets behave very differently as well. And although we're not going to cover it in this talk, helmet choice for an individual for the given speed and scenarios is also a really important component of trying to reduce overall drag. That's a little kind of introduction to the basis of aerodynamics. What I'm going to talk about now is just some of the ways that we measure aerodynamic drag. You often probably heard about wind tunnels and what they are, and they're amazing bits of kit. They've been actually around for well over 100 years in some shape or form. They've also got more sophisticated, but not hugely sophisticated, to be honest. The biggest kind of changes that we've had recently is just the accessibility, and the and how kind of automated the processes are to capture data and analyze it. So we kind of can have instantaneous, real-time feedback for athletes while they're in the wind tunnel, which helps them learn more about effective position and drag. But essentially, there's a few different types of wind tunnels. You've got open jet tunnels, closed circuit tunnels, low speed, which is really what we talk about, low speed wind tunnels versus high speed. So high speed would be kind of supersonic type things, for military aviation, that kind of stuff. We're looking at low speed wind tunnels, and this is the general construction where you have a test area here. You can see here, this is what we call a balance, which is essentially a set of scales, which is measuring the horizontal drag forces, and that's a simplified explanation, but that's essentially what it's doing, because the air is pushing against the cyclist here, and we need to measure how much force that's creating. And in this case, the turntable can move, that balance can move and give us different yaw angles, and as you can see, it holds the bike upright here. But essentially what's happening is, here's the inlet, there's a fan at the back here, which is drawing air, effectively pushing air out this way, and in turn it's pulling air in through here. There's various veins to get the air flowing straight and in a straight line, and then it exits here again. And this is all contained in a big housing unit, a big kind of hangar, if you like. So it's a contained, self-contained unit, but it's not a continual circuit loop that you get in some of the closed circuit wind tunnels. These are really the gold standard. They offer a high degree of control in terms of wind speed, in terms of measurement, in terms of repeatability. So that they're excellent. They're not quite real world. That's the only issue with it. You're not cycling on a bike. You're not moving around maybe to the same degree. It's very difficult to replicate the kind of resistance you get outside. So you're often not putting large amounts of power output down as well. But if they're used well and effectively with a good understanding of limitations, they're kind of gold standard, really. Another one that we often use in cycling is velodrome testing. The advantage of that is that you're actually cycling, you're creating your own air, if you like, your own airspeed. So you're capturing someone in their real environment. It's more difficult to control the environment. The repeatability is not quite so good. The sensitivity is not quite so good either. But effectively what we're doing is, rather than actually measuring the drag forces, back to some of those equations we looked at before, we've been able to account for all the other types of resistance, and measure the relative speed. We're measuring the power output. So effectively you're rearranging this, you're measuring all the components here. If we're measuring the total power output that's put out by the rider, we know we can estimate very closely in cycling the mechanical efficiency. We can calculate the kinetic energy and the potential energy of the system, and the wheel bearing friction we talked about, the rolling resistance we talked about, and the powers associated to overcome those. Then all we're left with is not knowing this. So we go back into that equation, we're measuring the wind speed here, and then we can essentially separate out CDA and understand what CDA is as a measure. So it's a really nice, neat little system, and it works very well. And often you'll do wind tunnel testing, and then kind of almost verify it and see if that's working in the velodrome. So these are really good systems as well. Use those quite a lot. There are a couple of other ways we can measure things as well. There's development of these kind of essentially pitot tubes here. This is there's a few versions of this out now, but these are attached to the bike, and effectively they're measuring wind speed. So very similar principle to what we're doing on the track testing, the last example. But now you can go anywhere, you can go outside as well. You're essentially measuring all the other factors, as well as the airspeed, and then you're back calculating what CDA would be. The other one is just various software you can use, where it will take a kind of effectively a GPS type file of an outdoor cycling, where it can measure the the speed, the road, obviously it's recording the road speed, and then it will look at the weather station data locally to understand what the wind speeds were locally. And then once you know the resultant wind speed and the various components, you can then just look at the relative wind speed and again back calculate that. But these two last ones, if they are done outside, some of the factors that have huge variation, if you remember back to that equation, is the rolling resistance. It's harder to understand the gradient effect as well, and the fact that some of your power might be used to overcome gravity. That can be accounted for to a point. But because of the variation, the small variations we're getting in, whether we're going uphill, downhill, what the actual surface characteristics are like, and the effects on rolling resistance, these two outdoors are not nearly as accurate unless you can very carefully control all of those inputs. So here just gives an idea of essentially which is most accurate, accessible, cost, and obviously the wind tunnel is probably the gold standard. It's highly repeatable. It's really not very accessible. There's only a few of those around. I don't think there's one. And maybe I think there's one in Ireland that could be used, but it's more research based. There's a couple in the UK that are available. Well, actually, probably one or two now. High cost, but can have a real impact on performance. And so you can kind of go through these and look and see, these ones are low cost. They're not very repeatable, but they're highly accessible. They're low cost, but they don't have a huge impact on performance at the end of the day. But they're useful tools nonetheless. So we've talked a little bit about aerodynamics, but also what we need to be aware of is actually, in reality for cycling, it's the cyclists themselves which cause most of the drag. We need to understand what happens when we change positions on the body. This is a really nice set of images from a paper by Barry and Burton, and the rest of them there you can see. But effectively, their bit of research looked at the different positions and how they change. So this is all pretty normal stuff that you might have seen out on the road. These images here of position relate to each other. So you can see a side-on view and then a front-on view. And you can see how this rider is effectively moving from the drops position, so the hands on the hoods to hands on the drops, to kind of tucking down a little bit, to moving to various things. Here they've got hands on aero bars. I think they're dropping the head at that point. Aero bars with a slightly different position, and so on and so forth. Head tucked down here. And you can see how this affects the kind of frontal position. So the frontal position, as well as the overall shape, is going to affect frontal area and then the coefficient of drag as well as other things. So just bear in mind some of that. We'll come back to it. I just want to show you now in this next slide how those two things interact. So remember we had C, D, and A, and often we can't separate them out. But when we measure frontal area, which you can do by image processing these days, that's generally how we do it, with a calibrated frame, you can then start to separate out the coefficient of drag from the area. And what we see here, so these are the positions, those 9 positions, and we'll refer back to that image in a minute to make sense of it. These are the CDA, so you can see how they generally change over time. So it gets from the kind of more upright position with the hands on the hoods, as the athlete comes down into kind of an aerodynamic position, you can see the CDA reduces quite somewhat. Okay, quite a lot. These are still relatively high values, but sometimes they do vary from place to place where you measure them, depending on your exact wind tunnel setup and all the rest of it. So we're more looking about the relative, more concerned with the relative change here. And in those positions, you can say actually the frontal area changes as well. It's quite high to start with, but as the athlete kind of lowers, it does change and get smaller. In fact, the smallest frontal area is that final position, number 9. Okay. We can also look at the coefficient of drag area. Sorry, the coefficient of drag now, because we've separated those out. We can actually, it doesn't change too much, but some of the subtle changes are quite interesting. And actually, if we look carefully, we've got a coefficient of drag at 6.694 in the upright position, and actually it doesn't go that much, that much smaller. We've got a position here, 676, which is actually the least draggy from a shape point of view. Okay, and actually this lower position at the front sorry, the very end in aerodynamic position, in terms of a shape, it's not actually as low a coefficient of drag as earlier on, but the frontal area is much different. And if we look from a coefficient of drag area perspective, when we look at all of these, we can see actually that the best position is not the final position here as well from an overall aspect. So here you can kind of see that we've got that's where the lowest CD is, coefficient of drag. That's where the lowest area is. And actually, when you look at both of them together, this is the best option, where we've got the lowest CDA. The power required to travel at 45 kilometers in this model is 358 watts, and compared to the starting position, the reference kind of position, that's 70 watts less than that starting one. So if we bear that in mind, position 3 versus 9. So if we go back to here, so 3, this is 3, there and there, okay, versus 9. So 3 compared to 9, you can see actually, look, this person is much lower down on the bike from here than here. Okay, very different. But actually, from a shape slipperiness point of view, in terms of that airflow and what it's sticking to or not sticking to in the stagnation, actually this more kind of upright position allows the air to move more freely around it. Okay, which is not uncommon. If you think about the air trying to find a way through the body without being stuck, without getting stagnated, you can see that this kind of more open shape may well be better from that perspective than this very closed kind of block where air might go in and get trapped. The difference is that some of these areas, this is a much lower frontal area than this one, as you can see, pretty visual, and we saw that in the data. So when you combine them together, actually, and look for the best solution, I think it was number 7 that was the better one here. Okay, where it's actually relatively open compared to here, but actually still a relatively low frontal area compared to this one, if that makes sense. So these things are really important to understand, and we can only really get an idea for this through wind tunnel testing or aerodynamics testing, where you can start to have a look at all the different shapes. And some people will just drive to try and reduce this frontal area, but not realizing the importance of the actual coefficient of drag as well. And this also shows us, when we're looking at improving aerodynamics, the role of the coefficient of drag. So even though we might say, right, well, actually, we're going to get in this kind of this optimal area, if we can change helmets, equipment on the bike, skin suits, those kind of things, then overall we might be able to enable the airflow overall over the whole system to be less retarded, if you like, not to get as stuck, so to keep the flow moving, and then overall we'll have a better CDA. I hope that makes sense. Here we can see another example. This is more kind of sprinting position, but you can see on the top left, this is kind of a regular sprinting position. If you think to watching kind of final sprint stages of something like the Tour de France, when they all get out of the bike and sprint, sort of get out of the saddle and sprint and move dangerously fast in these very narrow final road sections to the finish. This is kind of the positions they'll get into. Some people, and such as someone like Mark Cavendish, has really started to move into much more forward position. Then there's athletes like Caleb Ewan who have moved to that position even more. It's incredibly unstable and quite dangerous, but you can see what kind of happens in terms of, in terms of here, the changes in frontal area that you can get from moving from the kind of more upright position, if you like, to a more tucked position, and the changes here. And what we can see is how that change is really both in the males and females, the men and women, in terms of CDA, what that's caused. And you can see that, yeah, some of them, so if you go from the reference position to this purple one, this outline, small used here, is quite a big, like 26% reduction in the CDA. So it's worth doing, and particularly when you think about the speed that these guys go, or want to go, or have a huge, their power output will go a long way in terms of creating high speed. So reducing CDA is really important. So again, you can start to measure these things and help athletes find the best solutions, or at least support actions and decisions that they might take on the road. One of the issues we do have, and people often forget, is that actually when we change body position, we can also change function. quite considerably. So here's another series of images, and I'm not sure if you can, how well you can see them the size of your screens you're watching, but what this is kind of depicts is on the left-hand side, this is a kind of a relatively high trunk angle position, not dissimilar to cycling. I think it's 40 degrees at that point. 45 is fairly common actually in a road bike position on the hoods. So this is a 40-degree kind of trunk angle. And we can talk about go into detail about the various methods of measuring trunk angle and whether that's representative, truly representative or not, another time. But I think what you can agree here is if you follow that across, you can see that actually over time this trunk is reducing in angle. It's getting lower and lower. So we move from left to right. So we go 40, 30, 24 degrees, 16, and then I think it's 8 degrees is the final one really. But essentially you can see that's kind of almost a horizontal position. And as our understanding is of aerodynamics, as we just saw, that if you can reduce frontal area, then in general, depending on what happens to CD, your overall drag will reduce. So that's obviously, we see that in wind tunnel testing, and we'll find a position which is low in aerodynamics. But unless you've identified and understood exactly what's happening to function, you won't necessarily always get the best performance on the roads. But if you lower trunk angles, we can see here, there's an awful lot of research out there at the minute which essentially describes that when you do reduce that trunk angle, you have a reduction in power output, and particularly sustainable power over periods of time. So while you might reduce that power requirement, your sustainable power output is going to be reducing. So it becomes a balance of one against the other. And this is a bit of an unknown in most cases. Not many aerodynamic processes take this into account or measure it. But a good process would have a good idea of that relationship between trunk angle and power output and start to build that model for performance. And in terms of the factors that lead to a reduction of power output, well, we've got the changes in muscle activation patterns, we have changes in kinematics, and we have a change in the index of force effectiveness, which is effectively a measure of mechanical efficiency, really. So you might be putting the same amount of force onto the pedal, but you're not necessarily getting the same resultant or effective force out, which creates torque, which affects power output as well. So this is really important to understand and measure in cyclists and take into account as well. So it's very important. And effectively, what we're trying to do is create positions which are sustainable. So here's an example of an athlete, a guy I know actually, Phil. He's a well-known bike fitter actually. But this was him back in the kind of in the 90s, where this big expansion in kind of knowledge of and understanding of importance of aerodynamics started to come in. And so the strive was to get in these kind of crazy positions, really, that we know now. Everyone thought they were great at the time. But what you can kind of see here is a position where if you take the bottom bracket and you take a kind of a fairly vertical line up, you can see where the kind of the pelvis is. It's a long way back from that line. So you sat quite well backwards. You've got a very large drop to the aerodynamic pads. So you've got quite a lot of extension around the shoulder, which is quite uncomfortable for periods of time. But more than anything, you've got this severe kind of lower back flexion. And then you've got an awful lot of kind of upper spinal flexion as well. Now, both of those things become trigger points for injury, for damage, long-term damage. And in this position, as we know now, it's very hard to produce power outputs in this kind of position. You have a huge decrement. So you might be reducing aerodynamic drag, although a lot of the time back then that wasn't available to be measured very easily. But you're probably reducing power output. It's a very uncomfortable position and potentially a lot of long-term injury. And in fact, Phil now struggles to do many things because of the damage that was caused by doing too much time on his bike in that position. So we generally consider that to be kind of fairly unmanageable. Whereas a more kind of contemporary position would be something like this. This is Felipe Ganna, current world time trial champion, where actually if you take a vertical line from the bottom bracket, he is behind that vertical line, but not very far, certainly not back here. We have got a fair drop, but it's a much more kind of manageable position. He's got quite long forearm, so you don't necessarily always have that magnitude of drop. He's got a horizontal position, but it's with a much more effective kind of trunk trunk angle. Can be much more effective. We don't lose as much power in that position as we do here for those factors that we talked about earlier around kinematics, muscle activation, and force in effectiveness. And it becomes much more sustainable. And as we know now with aerodynamics and the use of kind of helmets and skin suits and better bike designs, all these kind of things, is actually we can go an awful long way with the aerodynamics as well as maintaining function as well. So what we're trying to do nearly all the time is have this balance between trying to minimize the aerodynamic drag, but also maximize the power output for that event duration. So whether that's a kind of a 4-minute event on the track to a 50-kilometer, 50-mile, whatever, if it's a triathlon event, 112 miles is it for an Ironman event as well. So just trying to balance those things, and comfort becomes an increasingly important factor, and some of that's saddle, but some of that's other things as well. And so there's a big aspect of positioning to make sure that we get a comfortable position, which is both low in aerodynamic drag, but allows us to optimize our power output as well for that duration. So what we're always interested in is having sustainable comfort and function, because they're critical to all of this as well. So if we were to create some fairly generalized guidelines for time trial positions, which is really kind of part of our job as sports scientists or applied scientists, if you like, is to translate what we know about the science and function of all aspects of performance into guidelines. This is what we're looking at really. So in general, and everyone's slightly different in terms of what's important for them in terms of both of these, both aerodynamics and biomechanics and function, is in general we need a low head position, but we don't want to force that position to be too low. It's got to be sustainable. We generally want a low trunk angle, but that becomes quite individual because of the links both to what that coefficient of drag is on that individual and the impact of someone's frontal area, but also on the biomechanics. Ideally, we have kind of narrow shoulders and elbow and hand positions, but again, it becomes quite individual because of what we understand about the coefficient of drag and having that airflow going through. The helmet shape, but also the interaction with the upper back is important, as we saw with that CFD work earlier. And in general, having a slightly rounded back position does help keep that attached, the flow attached to the body across its whole surface as much as possible. But these are generalizations, and really the only way you can optimize that is to do some of the wind tunnel testing for an individual. But if you follow those guidelines without them, you get quite a long way forwards. In terms of the biomechanics, here this is where we're trying to, as best as we can, optimize power and function at the same time. And so saddle height becomes very important for power, but if saddle's too high, it can also increase kind of the frontal area in terms of aerodynamics, the overall frontal area, and it may affect that kind of coefficient of drag as well, and just that shape of the back. We want that pelvis forward, move forward with some pelvic with forward tilt, as we saw in that last example. We want very little lumbar and thoracic flexion, and we want very little extension at the upper back as well, in the neck area. So those are really important things to take forwards, and some of those are primarily achieved by, in terms of position on the bike and the bike setup, is by a forward saddle position, and we also have to be mindful that the saddle choice and the actual tilt of the saddle angle is really important, so we're comfortable and stable as well on the saddle. Having hands slightly raised with forearms with respect to elbows, that's quite important as well. It can help for aerodynamics, but also comfort too, and also having a pad drop onto the aero bars, which is not too excessive, which is comfortable, and a reach as well that enables the above to be maintained as well, or achieved. So we're trying to have a position which is achievable and comfortable, and not limiting any of the kind of the power output and having a negative impact on the trunk angle. So those are the key things that we're really interested in trying to achieve. That is a constant process of adjustment adaptation, and when we're doing that, we need to be mindful of the kind of UCI rules, the bike and equipment constraints that we have that are available, and someone's individual constraints, because everyone's usually constrained to some point or not in terms of flexibility, mobility, function, range of movement, all those kind of things as well. Bit of a whistle-stop tour around things, but hopefully that's given you an idea. Those are some of the references that I'll leave on for a moment. So if this is recorded, you can actually grab them. Some references are referred to in there, but it's not comprehensive at all. And thank you very much for listening.